All right, so now we enter into an interesting point of the class where things get a little bit more mathematical. And so rather than trying to illustrate everything in animated PowerPoint presentations, we go to something a little more whiteboard style. And so, so already all of the kind of the handwritten notes that I use to develop the lectures are posted online in place of what would have before been PowerPoint presentations. But then I will also post my these slides from from our session along in the kind of captured area as well. So in the normal modules, when you go under Unit C, Lecture 4, you'll find the notes that I kind of prepared ahead of time. And then if you go to the captured sessions, which has the video recordings for these sessions, you'll find the notes that we actually had during. So if people ask questions and I draw examples and things like that, then that'll all be here. So that's kind of the way things will be set up. So it'll be a little different, but the last time I taught this class, that pivot to these handwritten apparently seemed that I got a lot of good feedback on it, that students felt that they could do more, that they could see more examples more clearly. And so that is something that hopefully will be a positive. So long as for some reason, my Zoom share doesn't keep switching away here. So, all right, so let's get started. So we are talking about cardinal social welfare in this lecture. And so we're trying to build up our intuition for cardinal social welfare and then end up motivating why we end up going with a kind of a Pareto approach, which we'll talk about next time, which will finally allow us to talk about economic efficiency in terms of markets, and not only the consumer surplus, which you've already seen, the producer surplus, this thing called deadweight loss, and how we can model externalities on this kind of supply and demand framework, so we can sort of start understanding like what exactly happens when you say put an emissions tax in and those sorts of things. So that's what we're kind of building up for, and it's kind of like the foundations of what we need to be able to sort of make a couple little mathematical arguments about how to deal with things like cap and trade and emissions taxes and things like that. So we've already sort of talked about utility functions. And so we have a basic idea of what a utility function is. If we want to say kind of more formally, and I noticed there that for whatever reason, the share didn't update. Let me see if Zoom killed my share for some reason. For some reason, Zoom on my tablet keeps dying. So hopefully this will work. If this doesn't work, then I may end up having to troubleshoot this offline and instead share the notes that I'm using, so there won't be the handwritten component until this gets fixed. So, which I'm kind of sensing that that's maybe a good idea for me to flip to, which is a little bit lame, and I apologize for that. I just wasn't expecting this issue. So one more time. Right over here, utility function. All right, so let's see how long this lasts. So we've talked about a utility function, which basically is a mathematical representation of a person's preferences. And so if I'm, we've seen that if I'm given options A, B, and C, if I prefer A over B over C, then in theory, I should be able to make a function, we'll call it U, that when you evaluate it on option A, it gives you a number. And that number should be greater than what you evaluate on option B. And that number should be greater than when you evaluate it on option C. And so And it looks like it's, Zoom has died on the tablet again. All right, so now this is gonna, just to save face here, then what we're gonna do is flip to, I'm gonna share my personal notes, and we're gonna treat them like these, like presentation slides, and discuss them as they go. Fortunately, in this one, I think the notes that I have for this lecture are pretty detailed, and so they should actually flow a bit like slides. They just happen to be handwritten. They're going to be actually clearer than my live handwriting anyway. And then by next time, I'll have figured out whatever this technical problem is. So, and I apologize for that. So let's share we'll share here. All right, so, and then maybe I'll make this one page there. Okay, so again, I apologize for this is kind of not ideal, but hopefully we can still make a good discussion out of this. All right, so we're focusing on, I'll use my little laser pointer here, the view hopefully you can see. So we're focusing on this utility function here, which is just, again, a mathematical representation of preferences. So we build a function, and that function could be, it could be something very objective, like it could be the amount of calories I get from eating raw food. And I might, need calories, and so I might prefer a higher amount of calories. And so regardless of what's in every food, you can boil them all down or actually burn them and measure how many calories are in every food. And so you might say that there are 30 calories in food A, 25 calories in food B, and 20 calories in food C. And so maybe you prefer the one with higher calories. Now, you might imagine that you prefer less calories, maybe you're on a diet or something like that. And so in those cases, then you could imagine that maybe I'm going to put a negative number in front of all of those calories. So now I've got negative 20, negative 25, and negative 30. Well, now that I've got that negative number, then this will flip all my preferences so that I'll prefer the one with fewer calories. So these utility functions try to find these mathematical tricks that capture our preferences, how we prefer one thing to another. And as we've already seen, that we can then create these spaces where there are a bunch of different options, which are represented as like these little dots here, and that we then can put options together that we're indifferent to. So if I give you A versus B, you always pick A. But if I give you A versus some option down here, let's say D, then you'll say, well, I'll take A or D equally. I don't really care. Either one is fine. And so in that case, I can draw a line of all of the options that are, say foods that you are happy to exchange for food A. And that becomes a so-called indifference curve. And this is all review of what we've talked about so far. So when you draw these indifference curves, you end up getting a set of indifference curves, and you can view them as like steps that you could step up. So this is like the lower step of a staircase. This is like a slightly higher step of a staircase, a slightly higher step of a staircase, and so on. As you step up this staircase, you get higher and higher and higher, and you reach towards greater and greater levels of utility. So that's, a way we model this utility. And then, as I was saying before, if everything has the same utility, they'll fall on the same line. So this is preference, and this is indifference. That's how we model that. So all that should be review. But I just want to make sure, are we all on the same page there before we get into types of utility functions and why we have to make things a little bit more concrete as we move towards the social side of things. Are there any questions on what we mean by utility function? I know it's a little abstract, but it's purposely meant to be abstract because it's supposed to bring us to a general framework for which we can talk quantitatively about how people prefer things. Okay. All right, I'll review so far. All right, so let's next slide as we would here. So we can group utility functions into different types. And so the first type of utility function that we sort of talk about are ordinal utility functions. And so this ordinal is a word that basically means we only care about order. So you can imagine that there are multiple ways that I could build a utility function that capture preference. And the question people asked very early in modeling people's preferences is whether it mattered, whether the actual numbers in the utility function mattered. So you can say, build a utility function, let's say A, B, and C. All we care about is modeling that somebody prefers A over B and B over C. Well, I could build a utility function, which however I calculate A comes up with a 10, however I calculate B comes up with a 5, and however I calculate C comes up with a 1. And those are all ordered as I want them to be ordered. But I could have also come up with a different way to order utility so that they're just ordered. So A is a 3, B is a 2, and C is a 1. And they both have the same ordering, even though the absolute value of the utility functions are different. In other words, you could imagine having the same indifference curves even. They might be spaced a little differently from each other, but everything that would land on the same indifference curve would still land on that indifference curve, but the actual spacing in the indifference curves may not seem to matter that much. So that was kind of the original question is, does it matter whether, does the scale and shape of a utility function matter? So it's kind of a big thing. So initially people assumed it kind of, well, it didn't, that these two utility functions are effectively equivalent because they capture preference in the same way. So I could ask you to rank your options, or I could ask you how good you felt about your options. And so long as your goodness feelings produce the same ranking, I could just replace your goodness feelings, your goodness scale with a ranking, and that would work just as well. So that's the idea of an ordinal utility function, is that it allows us to simplify the modeling of preference so that we can just keep track of the order of preference as opposed to the amount of preference. That's an ordinal utility function. The problem with that is that there are certain types of decision making that are not well captured by ordinal utility functions. And this is kind of a classic example called St. Petersburg's Paradox, which was put together by a guy named Bernoulli. And the St. Petersburg's Paradox, why St. Petersburg, that kind of has to do the history of how it came up. There's nothing especially, St. Petersburg-y about it. But what Bernoulli thought is he said, well, imagine if I give you a game. And I say, we're going to play a game, and we're going to start with $2 in a lottery pot in the middle of it, and we're going to flip a coin. If it comes up tails, you get whatever's in the pot right now, so $2 initially. If it comes up heads, then we're going to double what's in the pot. I will just put whatever money is necessary to double what's in the pot. So if it was $2, it'll become 4. Then we flip a coin again. If it comes up tails, you get the $4. If it comes up heads, I double it again, and we replay this thing over and over and over again. Now, eventually the coin is going to come up tails, and you're going to get what's in the pot. But it could come up heads for a long run of heads. And so that pot could grow exponentially. It could grow very large. So we repeat this until the first tails, and that's when the game ends, and then you get that money. But you have to choose how much you want to pay to go into this game to begin with. And if you just want to think about that for a second, how much would you be willing to pay for this? Actually, I might ask that question. So in the chat, how much do you personally feel that you would like to pay for this game? If I gave you this choice that you just pay me once up front, you pay me a certain amount of money, and then I then flip a coin a bunch of times, and every time it comes up heads, I double from an initial pot of $2. So $2 to $4, $4 to $8, 8 to 16, 16 to 32, 32 to 64, 64 to 128. So, every time it comes up heads, you get the pot gets double, and it just grows by a huge amount. So it's like a compound interest rate of like 100%, or something like that. How much would you be willing to pay for this game? The game ends when it turns tails. And when it turns tails, you just get whatever is in the pot. And so, so there's a question, is there no chance of actually losing? That's a good question. If you pay me $10 and it comes up tails initially or immediately, then I give you $2. So you actually kind of lost out there because you paid me 10 to win 2. So there is a chance of losing. The losing is that you're not going to win as much as you paid in. So does that make sense? All right. So I'd like to see a few more. I see a couple of survey answers there. So how much would you be willing to pay for this? You pay me once up front, and then we just go. And I also see people saying how much they would be under. That's a fine answer as well. If you just want to say, I don't know how much, but I know I wouldn't pay you X, that would be fine too. So either tell me how much you'd be willing to pay or how much you would not be willing to pay. Like what is a number you know you definitely wouldn't be willing to pay? That would be fine as well. So I'm going to wait for, I can wait. I'm going to wait for a couple more answers here. We got 33 people paying here. I see, great. Okay, great, excellent. Seeing a lot of good answers coming in. All right, so let's see what we've got here. If I just look through the answers here, we've got a couple of $5, $2, definitely under $10, $2, $4, $4, not 20. Definitely wouldn't go as high as 20. There's a comment here. If the starting pot's 2, so I'm not going to go any higher than 2. There's 5, 5, 5, 8, 5. So we're seeing a lot of under 10. And there's this comment about the starting pot being 2. I mean, on one hand, you say the starting pot is 2, so why risk losing? And I guess I guess in some ways you could say, well, why, if there's no, I guess what I should say is, what is a good price tag I should put on this? I guess that would be something that, maybe that's another way that I would put this, is this, if you were given a price tag for how much would you be willing to pay, given that I'm going to charge you that? So, yeah, so I think Jeremy's comment is excellent, where he said, if the starting pot is always 2, then I'm not going to ever put in any more than 2, because that guarantees I'm never going to lose. So 2 is a smart, thing in there. But I guess the question is, it is possible for me to refuse you. And so what if I put a price tag on it and I said, this is a $10 game? That's really what I'm actually asking you. Would you be willing to play the game? And that's what is the price tag that you would be willing to pay to play this game? So if that changes your answer, go ahead and update your answers here. But given that most people gave me a number above 2, then I'm guessing that's kind of what they were intending. So they're willing to accept a price tag on this game of $5, $8, $10, whatever. And so the interesting thing about this game is, if you look at the kind of statistics here, there's half of the time you're going to win $2. And then a quarter of the time you're going to win $4. An eighth of the time you're going to win $8, and so on. So basically 1 over n chance you're going to win in dollars. And so where those n's are just powers of 2. And if you end up calculating the expected reward from this game, it turns out it's infinite. So you can kind of see that, like, how do we calculate expectation? We just calculate an outcome times a probability. And we add all the mutually exclusive outcomes times their probabilities. So 2 is a mutually exclusive outcome times 1/2. 4 is a mutually exclusive outcome times 1/4, and so on. If we add up all of those things together, this adds up to 1. 2 times 1/2 is 1. 4 times 1/4 is 1. 8 times 1/8 is 1. If we add all those things up together, then we get an infinite expectation. So this is as an unbounded expectation. So there's no kind of central mass. Sometimes this game will give you gigantic rewards. So, but economic thinking at the time is that we should sort of price games of chance based on their expected value. And people should expect, or people should be okay with price tags based on expected value. So it's kind of like, say you're buying car insurance. and you're like, what price am I okay with? And you say, well, there's a certain chance that I'm going to get into an accident, and that's going to cost me a lot of money. But most of the time, I'm not going to get into an accident. So when you're buying car insurance, you're effectively saying, I've got two outcomes, not an accident, an accident. Not an accident is free, and it happens most of the time. Accident costs me a lot of money, but it doesn't happen that often. And so what you kind of do is you take the kind of the cost of the accident times the probability that the accident's going to happen. And then those two things together give you kind of the price tag you're sort of imagining you break even on if you pay for insurance. And so you might pay, I don't know, $100 a month. And that just means that over a 12-month period, you're willing to pay $1,200. And that's because you're not expecting to have an accident. But if you have an accident, you're kind of expecting it to potentially cost you $10,000. And if it costs you $10,000, but it happens, a tenth of a time, then that means that the kind of expected value there is about $1,000. And so maybe you're now willing to pay $1,000. You kind of feel like you're not being cheated that way. And so here, by that same reasoning, then all of the logic tells you that you wouldn't be cheated by any price tag. You should be willing to pay anything for this game. This game is that good. But in reality, most people, when they play this game, are not willing to pay more than, say, $25. And it turns out that really rich people are willing to pay $25. People with less money are willing to pay no more than like $5 or something like that. And so it also seems to depend on the person, but there is an upper bound and it is a low upper bound. And so, so that's what got Bernoulli thinking that ordinal utility may be simply ordering outcomes, because knowing that, well, it's better to have $8 than $4, simply knowing that it's better to have $8 than $4 is missing something. Somehow we have to deal with the idea that if you have $1 million, it's different than if you start with $1 million, winning $8 is very different than if you start with $2 and win $8. And so we value money differently based on how much money we have. We value outcomes differently as well. And so there is a way that it's more than ordering, it's the amount of value we put on outcomes. And so this kind of old way of thinking of this St. Petersburg paradox assumes that there is a utility function associated with money, where the money you have is on this axis and the utility you associated with that is just a linear function. So if I have $1, I get $1 of utility. If I have $2, I get twice the utility. If I have $4, I get twice that utility. And it just keeps climbing like a straight line. Now, the thing is, in reality, money appears to have diminishing marginal utility. If I have no money, then the first dollar might be worth a lot to me. So, we'll call the first dollar worth $1 to me. But once I have $1, then the next dollar isn't quite worth a full dollar to me in my kind of old dollar sense. So in order for me to feel that I've increased in wealth the same amount, I actually need maybe $1.50. Once I have $1 million, then getting $1, I may not even notice it. I might need to get $100,000 for me to start noticing it. And so my utility has this concave shape, this diminishing marginal utility here. And where if you start with a lot of utility, then the next marginal unit of utility gives you a marginal unit of the quantity, dollars, gives you not that much utility out of it. And that's what is kind of being modeled by this concave utility function. And it turns out that if you redo the probability calculations so that instead of saying winning $8, you say winning a utility of $8, and that utility has this concave shape to it, then you actually create a finite expectation where you can actually predict around a $10 expected utility. So it's the difference between expected dollars and expected utility. This game has like a $10 expected utility, which helps explain why people aren't willing to pay more than $10 to play the game. It's because people are discounting money in their heads, where once you have a lot of money, you then maybe discount the next dollar. But if you have very little money, the first dollar really matters. And so that implies that simply if all we cared about was ranking dollars, ranking outcomes, these two utility functions, the linear one and the concave one, would be the same. In terms of ordinal utility, these both order dollar outcomes the same. But apparently this one is more realistic. So that implies that we actually do care about the magnitude of utility change from one outcome to another. And so because the shape, the absolute value matters, then that suggests that ordinal utility is missing something. And so that's why we need to introduce something more complicated than ordinal utility. And that's the idea of cardinal utility. All right, so before I get into defining cardinal utility then, are there questions about this, this basic thought exercise, or what I mean by order not being enough? How these, from an ordinal utility point of view, these two utility functions, the straight line and the concave one, are the same because they both order outcomes, like winnings, the same way. But this one seems to be more illustrative of the way people actually act. So that means that the actual magnitude of utility increase from one outcome to another matters. Seems to matter when we look at real outcomes from people. Questions about that? And if you prefer, I can put in the chat, pardon my raspiness in my voice. So there's the questions link as well that you can feel free to pose a question to, although I don't have it up right now because of the technical challenges initially, but I can answer the question after the class as well. In fact, I guess I could open that link up. All right, so no questions about that. Everybody's clear on ordinal utility. All right, so what do we do instead? Well, in that case, that's when we introduce the so-called cardinal utility. So the word cardinal basically means that we're not just ranking things, we actually care about how different things are. So a cardinal utility measures the amount of difference between preferences. So the amount of difference matters. It's not just about the ranking. So rather than representing relative preferences, we're actually now, rather than having to ask you, is A better than B, we can say, how good is A? And then separately, how good is B? And then separately, how good is C? We should then be able to generate a ranking from that, but the actual absolute numbers that you tell me with the how good is, we can load into the cardinal utility function and start generating shapes that help better predict things like the human behavioral outcome in the St. Petersburg game that I just described. The problem with cardinal utility is measurability. It's much easier for me to ask you, do you prefer apples to oranges? But it is more difficult for me to say, you know, on a scale of 1 to 10, how much do you prefer apples? And on a scale of 1 to 10, how much do you prefer oranges? If I don't ask you those two questions together, I might get inconsistent rankings. So I might ask you about apples, and then we might talk about something else. You might forget that I asked you about apples. I might ask you about oranges. You might come up with a different number, and then those two numbers for the apple question, the orange question, aren't going to match up in terms of how you actually rank them because you kind of forgot that scale. So it's really hard to measure the how much type questions. And so philosophers kind of said, well, you know, what if you had a hedonometer? So, so hedonic, so it's, you know, like a measure of happiness or pleasure. And so imagine if you had this kind of hedonometer that was a sort of a hypothetical instrument that could measure your happiness like a thermometer measures temperature. And it turns out that now we're in the age of machine learning. People are building things that approximate hedonometers. And so they look at your facial features and other things, and they try to estimate how happy you are, just the same way you could put, you know, a temperature on your forehead and, you know, get a temperature out of it. And they're trying to measure that, you know. In a hospital, people ask you about pain scale. They'll say, how are you feeling today? You know, on a scale of 0 to 10, where 0 is I'm feeling great, and 10 is I'm in excruciating pain, and 5 is whatever. And they use that to sort of try to get an idea of the magnitude of how you're feeling. And these are good places to start, but in the end, they really seem like they might be effectively ordinal. Like they're really just looking for a way to rank. In the case of the hospital, are you doing better today than you were yesterday? Because we really don't know, like if I go to one patient's room and another patient's room, we kind of hope that your value of 5 as a patient is similar to some other patient's value of 5, but we don't actually know that you agree on what 5 means on the pain scale. So in the end, it's not that, you know, useful of a cardinal measurement. It really just seems like it's there to generate ordinal measurements. So what economists try to do is they like to ask things take a benefit perspective, you know, asking things, and this is some of the stuff that's intersecting with what you've been reading in the chapters, is how much are you willing to give up for a particular good? Or how much are you willing to pay, that's a give up, or how much are you willing to accept for me to take the good away? So, so the willing to pay question is that you don't have the good. And so I could ask you, for example, for a condor, you know, how much are you willing to pay to save a condor? And then if you say, I'm willing to pay, if it means one condor out there is definitely going to be saved, I will pay you $100. Then that tells me, at least for the first condor, you're willing to pay $100. And somebody else might be only willing to pay $2. Somebody else might be willing to pay it all. I don't really care about condors at all. The other thing that I could ask you is, alternatively, I could say there are 5 condors right now in California. I would like to kill all 5 of those condors. How much? But I will only do that if you give me permission to do that. How much will it take for you to give me permission to kill those 5 condors? And if someone says, you know what, I'd be willing to do that for $1 million, then that tells me that, you know, $1 million kind of gives me an idea of how much you value these condors. If you're not willing to do it for less than $1 million, then I know that 5 condors to you are probably worth $1 million. If I were to ask you how much would you pay to buy 5 condors, you probably wouldn't be willing to tell me $1 million, because you might not have $1 million in your back pocket just worth throwing around. And that's why these willing to accept questions are sometimes easier to ask than these willing to pay questions, because willing to pay questions are always kind of modulated by how much do you have available to pay. So whenever possible, an economist likes to ask a willing to accept question. So how much would be you willing to accept if I were to go out and remove this good? And so the amount that you're willing to accept to get rid of the good tells me how much you value that good. And so this is one way that I can kind of measure your cardinal utility. How much is what's cardinal you associate with certain goods. And this idea of surveying you, as you've already read about, I think, in your book, and we'll talk about a little bit more in different contexts moving forward, is this word called contingent valuation. It's the idea that I can survey you and ask you how much you're willing to pay or willing to accept. And so a survey-based estimation of value for non-market resources is contingent valuation. So if they're market resources, things that already have a dollar amount, I can use a revealed preference approach. So that's what I've said over here, revealed preference. And so if things are already out there, I could say, how much do you value an iPad that has a zoom that keeps crashing versus an iPad that doesn't have a zoom that keeps crashing? And so if these are both up on eBay, and I see that I paid so much for the iPad that had the crashing zoom and so much for the iPad that didn't have the crashing zoom, then I can infer a bunch of things. I can infer exactly what was revealed from those transactions is exactly how much the iPad is worth and the working zoom is worth. And so those two things together are revealed by looking at those exchanges. I didn't have to survey you because I can actually see what you actually did. That is a revealed preference. here is a stated preference, and survey-based approaches have these stated preferences. So it's still hard to get people to answer these questions, and so we trick them. And we do that by looking at real estate data. And so for environmental resources, they have an interesting property that environmental resources tend to be near homes. At least a lot of environmental resources are. So what we can do is we can look at a bunch of different homes across, say, the United States, and we can find homes that are matched in every way possible except for the environmental resource. So this home is exactly the same as this other home, but this home is parked right next to a wastewater treatment plant. And so the home that's parked right next to the wastewater treatment plant has to deal with all of the air pollution that comes out of the wastewater treatment plant. Whereas the home that is identical, that's in a different part of the city, is not parked next to that. If I look at real estate appraisals, so I ask an appraiser, so a professional who puts a dollar amount on homes to appraise both, this is a way of surveying that appraiser, or surveying the market, really. And if I see that there is a $10,000 premium on the home that is in the area that is not where the wastewater treatment plant is, then that tells me the value of clean air to this community. The value of clean air to this Phoenix community, for example, is apparently $10,000, because if you wanted to live with all of the other amenities plus pollution-free air, you would pay $10,000. If you don't really care about the pollution-free air, but do care about all the other amenities, you can save $10,000 and live next to a wastewater treatment plant. Now, of course, there's confounding variables, like other things tend to be around the wastewater treatment plant, so it's hard to find homes that are exactly identical. But if you take more sophisticated statistical classes and econometrics classes, then, and I guess I could put that term in here, econometrics, and just more statistics, so these are generalized linear mixed models statistics. And so there are statistical methods that you can learn that help you tease away all of these confounding variables, so that if you look at enough houses, even though two houses are never identical in everything but the natural resource or the environmental resource, what you'll find is enough houses differ in enough ways that you can subtract out the effects of everything that aren't dealing with the environmental resource, and then find out exactly how much the environmental resource is worth. So that's the modern way to do stated preference, these kind of contingent valuations, is through real estate appraisals. So that's how we can start estimating the cardinal utility of an individual, or for an individual. So before we then scale that up to thinking about how we put groups of people together into cardinal social welfare, which is really the focus of what we want to move into, I want to make sure that we covered, are there any questions here about this idea of cardinal utility, how it differs from ordinal utility, and all of the different ways that we could potentially measure cardinal utility using survey and market-based methods? Any questions? Maybe while you're thinking of questions, maybe let's do an attendance question. So for those watching the video, maybe what I'll do here for the attendance question is I will put a little marker here with the attendance question link, and I'm going to drag this in. I don't know. Let's see, the way I've shared this, can you see a sticky note on top of my notes right now that says attendance question? The way I've shared this, and you may not be able to. So if you can or cannot, let me know in the chat. Do you currently see, okay, no, great. All right, so so let's do this then. Where did my Zoom go here? So let's share this screen. So sorry that I don't have the QR code, but so nice marker in the video that we are at an attendance question. And so the attendance question that I have here, which I'll put in the chat here, is what is a modern approach at estimating environmental resource value that goes beyond simply surveying people with WTP and WTA questions. So we just talked about it, the kind of modern approach to contingent valuation, although we do still survey people, but we fortunately have a way that we can estimate the value of environmental resources by using survey data that's kind of already baked in to data that is widely available as you look across space, across where people live and things like that. So that's what I want to put in the attendance question. And so again, I'll put the URL up there in the chat. All right, so now I will go back to the old share here, which is here. All right, let me know if you can't see the old share or the back to the slides. All right, so any other questions about cardinal utility at the individual level? Oh yeah, there will be at least one more question, so don't submit now. Same as usual, just put it in the top answer and just let it sit there in a side tab, and then I'll submit at the end. All right, cardinal social welfare. So the idea is that we want to be able to measure collective welfare. So part of the reason we needed an absolute scale at the level of individuals is we sort of need a way to combine individuals together. Just like in that hospital, I need to make sure that the pain scale in one room kind of matches up to the pain scale in another room for me to be able to compare how people are doing. So if a doctor comes to, let's say, a nurse and asks the nurse, how well are people doing on the floor? The nurse needs to have a way to sort of say, to be able to prioritize and say, this person is in far more pain than this other person over there. And having a pain scale that is agreed upon across people makes it easier to do that. And that's kind of what cardinal utility did, is it tried to give us a scale that allowed us to compare across people. So we can sort of say that if this person over here in this room said they're on a pain scale of 9, really in pain, and this other person over here said a pain scale of 2, then we'd say, we care about this person over here that has a pain scale of 2, but we might want to prioritize our help to the person over here at a pain scale of 9. Now, if we weren't careful about the way we defined our cardinal welfare, then this 9 might be equivalent to this 2, or this 2 might be greater than this 9. So that's about calibrating these things. We hope to have the ability to be able to normalize so that this cardinal social welfare allows us to kind of figure out how to handle policies that affect groups of people, if that makes sense. And so we can scale up from thinking about the welfare of a floor of a hospital to thinking about the welfare of a society. And so how would we measure an aggregate social welfare for a society? So on the hospital floor, we might say, what's the average pain scale right now? And we can say that on average, people have a pain scale of 3. And a doctor might say, hey, that's pretty good. So for this floor, there's not a lot of people in a whole lot of pain. So I, for now, am going to, on my rounds, maybe come back to this floor later, but for now I'm going to go to a next floor because I think that everybody on this floor has got it handled. They go to another floor, they find out the average pain scale of 8. And that tells the doctor that maybe they need to intervene and find out what's going on that floor. So having these aggregate measures of social welfare for the floors tell us how to change our policies. And so aggregate measures, for example, in economics, might be things like life expectancy. So you can ask, what is the life expectancy of a group of people in, say, in a country, in a city, in a particular region of the city? You can say, what is the average life expectancy? And so I use this initialism here, LEB, life expectancy at birth. This is just a common way to estimate life expectancy. So when you're born, what's the, how long is it until you die from after you're born? And you could say I've got in individuals. So, so this is the total number of individuals in my society. If I take this person, might live for 100 years, this person might live for 20. If I add up all of these together and I divide by n, then I get an arithmetic mean, which is the representation of my average utility, my average social welfare in the group, life expectancy at birth. So it has this kind of structure to it. So that's one measure of cardinal social welfare. It's the how well is the group doing? It's the average life expectancy. Another common one is per capita income. Per capita income is the average income over a group of people. So per capita means we're just dividing by the number of people. So some people make $1 million, some people make $20. You add them together, and then you say on average how much do people make. Now, that last example I gave you, $1 million versus $20, I hope you see that taking an average there seems kind of like a crazy way to measure welfare. Because if one person's making $1 million, yeah, they're doing great. If another person's only making $20, over, I don't know what time period we're talking about, but, over a year, then we know that person is really poor off. And so taking the average of those two, we'd say, well, that's basically $1 million divided by 2. That's suggesting that the average social welfare is $500,000, which sounds pretty good. But in reality, there's somebody that number loses out on someone, the one who's only making the 20. So that suggests that the way that we add these things up and just simply divide may actually affect the way we properly choose policy. So we may need to somehow add in other mathematical functions that help us better understand the distribution of utility among those individuals. And so an example I've given here is this is a one that was proposed where we take the average income, so it's our per capita income, and we multiply it by 1 minus this thing called a Genie Index or a Gini coefficient. Just to see how many people are paying attention, how many people have heard of a Genie Index before, maybe in some of your other classes, or a Gini coefficient? Okay, all right, interesting. Okay, great. That's fine, no worries. So a Genie Index is it's kind of outside of the scope of this class to tell you how to calculate the index, but I can tell you what it means. And so if I take a distribution of wealth across individuals, if every individual has equal wealth, then the Gini Index is equal to 0. And so what that, and then if I take a distribution of wealth across people, and if all of the wealth is held by one person and everyone else has 0, then in that case, I have a Gini coefficient of 1, a Gini Index of 1. So it might be that both of those distributions have the same per capita wealth, but the one where everyone has an equal amount of wealth is going to have a more uniform distribution. So that has a Gini coefficient of 0, but the one where even though the per capita is the same, but all the wealth is held with one individual, that has a Gini coefficient of 1. So a high Gini coefficient tells you that you have a unequal or non-uniform distribution of wealth in a society. So you can go through and you can measure the distribution of wealth. And you hear this stuff all the time, 5 percenters, 2 percenters, 1 percenters. That phrase means that this is that it's representing that only say, you've probably heard of people talking about, and I'm sorry, my phone is ringing and that's in my ear. So even though my phone is silenced, if we were in person, then in my ear, it's driving me crazy. So I apologize for that. And I have accidentally flipped away my phone app in my panic. All right, apologize for that. So so we can calculate Gini coefficients from real data. We can actually say, what is the Gini Index for United States? You can look this up. If you Google Genie Index, you'll find Gini indices across India, United States, Russia, UK. You know, it's all been kind of calculated, and that tells you kind of how equal the distribution of wealth is. And in areas where it is higher, then that means that there is a small number of people that have all of the wealth. And so you can imagine if I can calculate that and I can calculate average income, then maybe what I'm going to make is my choice of social welfare function is not the per capita income alone, but it's a per capita income times 1 minus the Gini Index. And what that tells me is that I care both about how rich my country is per capita. So that's the per capita income, how rich we are as a group. But I also care about how shared that wealth is. And so what this is saying is, even if I'm really rich, if the Gini Index is 1, which means that all of that money is held with one person, then this thing that I'm multiplying it by is going to be equal to 0. And so my social welfare function is going to be 0. It's going to say I'm going to have no social welfare. Even though we have a lot of money, I've discounted that money because all the money is held by one person. And so on the flip side, if I have a lot of money and we all have equal money, so we're all sharing equally in that, this social welfare function would end up amplifying that effect so that we're saying we have really high social welfare. So what I'm trying to get at here is your choice of social welfare function reflects the priorities of your society. So if you choose to measure per capita income alone, what you're saying is you do not care about the distributional effects of your policies. You don't care if all of your money is all with one group or if it's spread out among many groups. If you instead measure something that includes distributional effects in it, then you're saying that you're going to give some bonus to spreading that wealth out. And so we can make different choices for these social welfare functions is what I'm trying to get at there. So before I go into the types of families of social welfare functions, which is really going to play into the homework, there's a new homework, by the way, that's been available out there. The rubric still needs to be updated for that homework, but the homework is out there, and I think you've got about 2 weeks to do it. And the content of that homework will be the content we're going over in the next couple lectures, and will be the content we'll see on the midterm in, I think, late October. We'll be part of that content, not all of it, but we'll be part of that. But it'll kind of be the most advanced part of that midterm. So are there questions about this basic motivation for what the realistic cardinal social welfare functions are that we use in real, this is getting kind of closer to macroeconomics, where we're actually measuring aggregates for large groups of people. Does this make sense? And is it clear how an economist's choice of what they're measuring of how things are doing is going to be is going to change the way our policies shift. The same way a doctor saying what's the average pain scale might miss that some people are in huge amounts of pain while others are in no pain. And the doctor could have asked, like, what's our pain index? And the pain index might be the average pain times the Gini coefficient of the floor, 1 minus the Gini coefficient. And then that would tell the doctor if everybody's feeling the same pain or if there's huge distributional effects. Questions? Anything? All right, great. All right, so basically, now that I've motivated that there are different types of social welfare functions, at this level in your economic education, it's a good idea to sort of figure out what are the basic classes of social welfare functions, and what do the choice of functions from those classes mean about kind of what you're emphasizing as is what's important in society. And so, so the first kind of example of that is the so-called Benthamite, named after Jeremy Bentham, who's sort of an important thinker in utilitarianism. So the Benthamite utilitarian social welfare function. And I've put it down here where it's just the social welfare is just equal to, and these are constants, I just put little Greek letters, alpha 1, alpha 2. So alpha 1, U1, where U1 is the utility of individual 1. And alpha 1 is a number between 0 and 1, or actually it's just a number greater than 0. It doesn't have to be between 0 and 1. So it's a number greater than or equal to 0. And it scales the utility of the individual associated with it. So if we have n individuals, we're going to have n of these indices. And that allows us to say that one individual is slightly more important than another individual, for example. So you can say that the alpha value is equal to 1 for this individual, but it might be equal to 50 for this individual. So we're saying that this individual's utility is somehow 50 times more important to us than this individual's utility. And so this social welfare function, if we were to plot indifference curves, we would do that where we would put the individual utility on one axis and another individual's utility on another axis. And the indifference curves represent exchanges of utility between those individuals that come up with the same social welfare. So this is kind of like a doctor goes to the floor and they say, what's the average pain index? Well, if you say 5, that might mean that you have 2 individuals that say, I have an average pain of 5. Or that might mean one individual's at 0 and the other individual's at 10, and their average is equal to 5. Well, those would both be on the social welfare function of 5. So I could say that, you know, if you both have a pain index of 5, if I take all the pain away from one and give it to the other, so that now they're up to 10, I'm saying from my social welfare point of view, that's equivalent. I'm saying that I don't care the difference between those two. And so that's what an indifference curve means here, is that if we exchange utility, so we take how someone's feeling away from one person and give it to someone else, then what amount of exchange do we do to sort of not change our social welfare? And then the collection of all of those ones that we're indifferent to form our indifference curves, just like before at the individual level when we had goods on the different axes. And so we get indifference curves that are lines, parallel lines, where the slopes are determined by these coefficients. So if I only have 2 individuals, so that would just be the first 2 terms here, then I would get this picture here, where this slope would be whatever the alpha 2 coefficient is divided by whatever the alpha 1 coefficient is. So if these are equal numbers, then these would be 45-degree lines. If they're not equal numbers, then they're slanted, and they might be slanted to favor one individual or to slanted to favor the other individual. And so that's what we're capturing here. Now, there are 2 special cases of Benthamite utility functions. Either where you set all of the coefficients equal to 1, in which case we are just summing up all of the utilities. And that's either called a strict utilitarianism social welfare function, so strict utilitarian social welfare function, or we might just call it the total utility social welfare function. So if we want to maximize total utility, or maybe we want to minimize total pain, or we want to maximize total income, then that is what we're modeling here. A slight variation to that are the averages that we saw on the previous page. And so whenever you take a per capita, or you take an average life expectancy, you are taking a Benthamite utilitarian perspective. You are saying that you are going to take the utilities, the life expectancies, the incomes, and you're going to average them across. And that's equivalent to setting all of the coefficients equal to 1 divided by the number of individuals. So I can simplify that just by saying 1 over n out front here, and it looks like the average. But that's the same thing as setting all the coefficients equal to 1 over the total number of individuals. That's what's going on right there. And that's so the average and the strict utilitarian, both of those are just special cases of Benthamite. And both of these cases are just going to give you diagonal lines that have 45-degree angles. And so they are going to have this equal respect condition, which I'll remind you of in a couple of slides here, but they won't be favoring one or the other. They'll just be the same 45-degree angle all the way up through the space. Any questions there on what I mean by a Benthamite utilitarian function? This idea of social welfare where you're just adding the individual welfares up and then scaling them by these coefficients. That makes sense. Sometimes people just refer to this as utilitarianism because it's kind of the simplest approach. Okay, great, all right. Potential problems of Benthamite utilitarianism. I've already illustrated some of these in the kind of pain examples and things like that, is that I've given these examples here of 3 individuals. In this case, one of them has no money, one has 100, the other has 50. In another case, they all have 50. In another case, one has 150 and the other 2 have 0. And so if I just base this on total utility, then all of these have the same total utility. And because they all have the same total utility, they all have the same social welfare. So if I were to walk into a hospital floor and these are very different distributions of pain, or if I were to walk into 3 different countries, these are very different distributions of income. And yet I would view as things saying, this is the same. All these 3 countries are the same. There's no need to make a change because all these 3 countries are doing just as well. So that is maybe not, if we care about distributional effects, so we care about the distribution of utility, this maybe isn't the right utility function to use. Or functions like life expectancy and per capita income, those do not care about distributional effects because they're Benthamite. And because they're Benthamite, if we care about distribution, we need something more sophisticated. So an alternative to that is the Rawlsian or Maximin social welfare, named after, sadly, an old white guy named Rawls. So I'm not going to tell you too much history about these because why do we need to stress a bunch of old white guys? But they just traditionally are called Rawlsian social welfare functions, or Maximin, for reasons which hopefully will become apparent here in a second. So here, rather than adding up the utility and saying that's our social welfare, Rawlsian took the other extreme, or Rawls took the other extreme approach and said, well, what if we just say, we're going to look across all individuals and say who's doing the worst? So our social welfare is the utility, is the welfare of the worst off individual. We ignore anyone who's doing better than the worst off individual. We take the minimum across all individuals. And when you do that, you get indifference curves. So we've already seen an example like this when we were talking about a consumer choice theory with different goods that look like these angles here. So this is an indifference curve with a society where the minimum individual is doing better than a society over here. And so they look like this because in this region up here, the individual indexed 1 is doing better than the individual indexed 2. And so all of the social welfare is determined by the level of welfare on this dimension, the individual 2 dimension. And that's why the social welfare functions are vertical. Over here, they're horizontal because in this region, then this is the region where individual 2 has a greater utility than individual 1. So in this case, all of our utility is based off the utility of individual 1. And that's what we're saying. This is what I'm trying to write here. I1 is equal to U2 when U1 is greater than U2. I probably should have wrote this over here to make that a little less confusing. But you end up getting these, when these horizontal and vertical lines come together, you get these nice right angles. All right, so does that, that is another way. So imagine if a macroeconomist went and they didn't ask what is the per capita income in the United States. Imagine if they asked what is the minimum income in the United States. And imagine if we hung all of our economic policy on that. How different would our economic policy be? mean, imagine that if the only thing we could brag about, the only thing we were allowed to brag about is how well off the minimum income was. We would have a totally different set of policies than we do now. So that really shows you how the choice of social welfare function changes the way in which we look at policy. Now, you might say that's way too extreme, Ted. It doesn't make sense. They're never going to take the minimum of all that. Well, I have the utility function for you then. I have the social welfare function for you. And that's the so-called egalitarian social welfare function. And this is, oh, I'm sorry, there was a question. Do I think policies will be better or worse if we use the Rawlsian utility function like up here? That is an excellent question, and that is a question for a normative economist. And so a normative economist might take the stance that it would be better if we use these utility functions that strongly prioritize distribution, like the Rawlsian. And they might suggest that when we're making decisions about climate change or whatever, then that's the utility function we should use. I am not going to tell you my personal preference, because I'm just kind of surveying through these. But as a positive, or sorry, as a normative economist, then that would be a choice that you'd have to make. You'd have to take a stance and say, we need to use this utility function or that one. And here's my argument for why we need to use that. And your argument for using the Rawlsian might be that you think life would be better off for society as a whole if you use the Rawlsian. Someone else is going to make the argument that actually distributional effects don't matter for X, Y, and Z, so we should be using a per capita approach, a Benthamite approach. And so, you know, reasons for each, they're very subjective. And that's the role of kind of normative economists to kind of figure out that. But it's a good question to ask. Right, so the other utilitarian function, you know, this is the kind of mix of those two, is the egalitarian. And so I'm going to introduce this constant, which this is my notation, but lowercase m is the minimum. So this basically is the Rawlsian utility function here. And what I'm going to do is I'm going to take total utility down here, and I'm then going to subtract this this coefficient here, which I just called lambda. So it's a number between 0 and 1. And then that is multiplied by the sum of everyone's difference from the minimum. So because it's the minimum, all these numbers are going to be greater than 0 or greater than or equal to 0. And so this sort of allows you to build in a distributional component on top of the kind of total component. And so as you crank this lambda from 0 to 1, what you end up doing is you end up moving from strict utilitarian all the way to Rawlsian. So this social welfare function, when lambda is equal to 0, then it ends up being straight parallel lines. It is the total utility function. When lambda is equal to 1, and you can do a little exercise to prove this to yourself, but when lambda is equal to 1, after you do some algebraic recombination and things like that, then this turns into the Rawlsian utility function. Basically, you set this lambda equal to 1, and all of the u's are going to cancel with all of these u's, and all that's going to be left is effectively maximizing a minimum, and that's the Rawlsian, the maximin. And so when you set this lambda equal to 1, the indifference curves are going to be those right angles from the previous page. Anything in between gives you utility functions that look like this. They have kind of these shallower angles that meet at the diagonal line and have a little bend there, a little knee here. So this is the so-called egalitarian, which is meant to allow you to program your mix. So if you like say, I'm 50-50% total utility and 50-50, you know, some 50-50 total utility and Rawlsian, then this allows you to mix those two. All right, we only have 5 minutes left, so I just want to make sure I at least cover the last utility function here, and that's the Cobb Douglas social welfare function, which looks a lot like our diminishing marginal returns ones. And it kind of is an alternative way to impose this egalitarian pressure without this lambda value. So rather than having to decide on lambda, you kind of, what's nice about this one, which is just the product of everyone's utilities. So no extra parameters, it's just the product here. And what's nice about that is when things get crazy, where one individual starts gathering up all the wealth, then it starts acting like a Rawlsian. These become vertical lines. When everyone starts sharing an equal amount of wealth, then it starts acting like total utility. So the cool thing about a Cobb Douglas social welfare function is once we're all doing equally well, then it prioritizes us all doing better. So collectively in the kind of per capita way. But when one of us is doing a lot better than the others, then it actually prioritizes a shift in distribution toward us becoming more equal. So it kind of is the best of both worlds in a kind of a different sort of way here. So that's the Cobb Douglas. All right, so just the last couple of things, there's two definitions that I want to make sure that we see, and that's the equal respect condition. I talked about this in the last lecture, and that's basically if two individuals swap their pain scales, the doctor looks at them the same way. So if there's symmetry, so if you were to fold the utility function across the diagonal axis and get the same indifference curves, then you have the equal respect condition. So that means that no individual is favored over another. So a Benthamite utility function, when you favor some individuals over the others, does not meet this. But total utility does, and the per capita does. Any one of these things that were symmetric across the diagonal meet this condition. And then the last condition I want to spit out here before asking for questions is inequality aversion. And so inequality aversion is basically the convexity of these indifference curves of the social welfare function. And so inequality aversion is this idea that we favor distributions that are more equal than distributions that aren't. And so that relates to if we assume a concave individual utility for money, where individuals don't get as much gain if you're making a lot of money, we're basically saying you don't need a lot more utility. It's going to take so much extra money for you to get extra utility. We're going to forget about that, and we're going to focus then on those who are earlier in their curve. If everyone has this concave utility function, then naturally when you put them together, you get something that looks kind of like a Cobb Douglas. So, but in general, if you have something that bends towards the origin, then that has this inequality aversion. And so the total utility function does not have strict inequality aversion because it does not bend towards the origin. But the Rawlsian does, because that's got a really strong bend towards the origin. The Cobb Douglas does, because it's got a bend towards the origin. The Egalitarian does, because it has a bend towards the origin. So anytime that these indifference curves in joint social welfare space bend towards the origin, so in other words, are convex, they have what's called inequality aversion. They tend to prefer distributions that are more equal than distributions that aren't. And then my last slide here is just a comment that I've already sort of beaten you over the head with this, that the choice of utility function is sort of a choice of objectives for your society. So there's a role for normative economics there, but that's also the weakness. And so next time we're going to go back into the Pareto effect, Pareto perspective, which kind of allows us to not have to make these cardinal social welfare choices and still be able to get mileage out of social welfare. So what are alternative social welfare approaches that don't require us to make cardinal welfare stances like these? So you should know about these, but we're going to move forward hopefully without having to assert a social welfare function. All right, so we're at 1:15. So let me give you an attendance question and then happy to take any questions about this material. So the attendance question link is in the chat, and I'll also put it here in this sticky note, which I'll share again. If I can find my share, new share, sticky note, attendance question there. All right, so the last attendance question for today is give an example of a social welfare function that does not have the does not have inequality aversion. So what is an example of social welfare function that is not sensitive to distribution, that does not have this convexity of pulling towards the origin? And with that, that's all I have for you today. And hopefully I'll have the tablet issues fixed up by Thursday. If there are any questions, I'd be happy to take them.
Thanks so much.
Yep. Oh, I see. There's a question. What is the main economic principle that the US follows, if any of them? And I think that depends on the question you're asking. I think there are some economists that study certain, it depends on, are you studying fisheries? Are you studying the wealth in cities? Are you studying the wealth in in rural areas? Like, so kind of depends on the types of questions you're asking will kind of tell you, like, do you care about distributional effects or not? And so, if every time you hear somebody talk about GDP, GDP does not focus on distributional effects. It's just adding up a bunch of exchanges. And so that's an example where I'd say, well, that's kind of more of the Benthamite perspective. But this Genie Index, if you Google that, you'll find a lot of people use Genie indices to rank countries. And a lot of people care about that. So it just depends on the person and the problem. Any other questions? Thanks for your patience. I really appreciate it with the technical problems. And we'll work on that next time. Was not expecting the Zoom crashes.
Yeah, I got a question about the inequality aversion. I'm still trying to think of an example for the last attendance question, and I'm hitting a blank on it.
All right, so basically, I guess what I'm saying is that, oh wait, I don't have that screen shared, is that if you were to look back over the social welfare functions that I presented, which ones of them are not strictly convex? Like, which ones of them are not bent like the left-hand side of a U? And there was one in particular that looks more like a V than a U. It looks like the left-hand side of a V than the left-hand side of a U. And that's the one that I'm kind of looking for there. So that one, because it is not bent, it's not dented towards the corner of the joint social welfare space, then that's the one that does not have this inequality aversion.
Okay, just making sure. All right, thank you.
Mm-hmm. And the other way to say that is, I've mentioned a couple of times that a particular social welfare approach does not favor equality. It just doesn't care about how equal the distributions are. And that's the one I'm looking for. Like, that approach where you just don't care about distributional effects, that's the one that does not have inequality aversion. And thanks for the feedback in the chat. Appreciate that. Any other questions? All right, looks like we are kind of at an anti-quorum here. So I will go ahead and end the meeting and see everybody again on Thursday. Have a good week.